In the early hours of February 24, 1979, something moved deep beneath the state of Utah. No one felt it. No buildings shook. No dishes rattled off shelves. The entire event registered at just magnitude 3.8, small enough to go completely unnoticed by the 1.2 million people living above. But the seismograph stations at the University of Utah recorded it. And when a young postdoctoral researcher named George Zant sat down to analyze the data, he found something that stopped him cold. The earthquake had originated 90 kilometers below sea level. Not 9 kilometers, not 19, 90. That number was not just unusual. According to every geological model that existed in 1979, that number was impossible. To understand why, you need to know something about how earthquakes actually work and where they are supposed to happen. The outermost layer of the earth is called the crust. Under continents, it runs roughly 30 to 50 kilometers thick. It is cold, brittle rock, the kind of material that can fracture under stress. When tectonic forces pull or compress or shear that brittle crust, the rock eventually snaps. That snap is an earthquake. Below the crust lies the mantle, and the mantle at depth behaves nothing like the brittle material above it. Under the enormous heat and pressure found 70 to 90 kilometers down, rock does not fracture. It flows. On geological timescales, it moves more like an extremely slow, incredibly thick fluid than a solid. Professor Keith Popper, who would later lead the team that revisited this mystery, described it simply. He said the mantle rock at that depth is more like taffy. Taffy on timescales of millions of years. Taffy does not snap. Taffy does not generate earthquakes. That is the rule. The mantle flows, the crust breaks. Earthquakes happen in the crust. This was not a contested point in seismology in 1979. It was foundational. And yet George Zant's numbers placed the 1979 Utah earthquake 40 kilometers below the bottom of the crust, deep inside the mantle, where earthquakes were not supposed to be physically capable of occurring. Zant did the analysis multiple times. He checked his methods. He wrote up his findings and published a short abstract in a journal called Earthquake Notes. Then he moved on with his career, eventually spending decades on the geology faculty at the University of Arizona. The 1979 Utah event sat quietly in the record books, classified as anomalous, unexplained, and largely forgotten. Science has a category for things like this. They are called outliers, and outliers have a way of waiting. They wait until the tools improve, until someone new looks back at old data with fresh methods and better equipment, until the anomaly accumulates enough company that it can no longer be dismissed as a fluke. That process began slowly over the following decades. Between 2007 and 2010, researchers in Utah identified 6 more suspected deep seismic events in the same general region of northern Utah and southwestern Wyoming. Their depths were unusual too, each one originating well below where the crust ends and the mantle begins. Each one lacking the aftershock sequences that typically follow crustal earthquakes. Each one isolated, brief, and strange. The boundary between the crust and the mantle has a name: the Mohorovičić discontinuity. Seismologists call it the Moho. It is not a sharp physical wall but a transition zone, a depth at which seismic waves change speed because the composition and density of the rock changes. Above the Moho crust, below the Moho mantle. Every one of these suspected deep Utah earthquakes have originated well below the Moho, in some cases more than 20 kilometers below. Then in 2024, a new team of University of Utah seismologists, led by geology professor Keith Popper, decided to go back to the beginning. Back to 1979. Back to George Zant's original data. They reanalyzed the seismic waveforms from the 1979 earthquake using modern computational tools that simply did not exist when Zant first examined them. They applied updated velocity models of Earth's interior, better understanding of how seismic waves propagate at different depths, and methods for separating genuine deep source signals from the kind of noise that can mimic deep origins. Their conclusion confirmed what Zant had found 45 years earlier. The 1979 Randolph earthquake was real. Its depth was real. 90 kilometers below sea level in the upper mantle, beneath the continent, in a place where nothing in the established geological framework said an earthquake should be possible. And it was not alone. Koper's team confirmed all 9 suspected deep events, the 1979 earthquake, and the 8 others identified between 2007 and 2023, all originating well below Earth's crust, all clustered in the same region, all sharing the same unusual characteristics. No aftershocks, isolated occurrence, and a focal depth that placed them firmly in what should be ductile, flowing mantle rock. The team gave these events a formal name: continental mantle earthquakes, or CMEs. That designation matters more than it might initially sound. A formal category means these are not flukes. They are not data errors. They are a real class of seismic events that the existing models of earthquake generation did not account for, and that scientists now need to explain. Study was published in the Seismic Record in June 2026, and almost immediately, the question it raised was the same one that had stopped Zant cold in 1979. If rock at 90 kilometers depth flows like taffy, what is breaking? The research team has a working hypothesis. The earthquakes appear to cluster near the edge of what geologists call the Wyoming Craton, an ancient, cold, thick section of continental lithosphere that has remained stable for over 2 billion years. The craton's root extends much deeper into the mantle than surrounding rock, and its boundary creates a zone where temperatures and pressures change sharply over short distances. Near that boundary, mantle flow, the slow, convective movement of rock over millions of years, interacts with the cold, rigid edge of the craton in ways that may generate localized stress concentrations. Stress that builds slowly over geological time in rock that normally flows, until in certain conditions it reaches a threshold and fractures. Not taffy flowing, taffy snapping. The conditions under which this happens are not yet well understood. The process is not mapped. The geometry of where future events might occur, how frequently they occur, and critically, how large they can get, remains almost entirely unknown. That last uncertainty is the one that carries real implications beyond academic geology. When seismologists assess earthquake hazard for a region, the likelihood of damaging ground shaking, the risk to buildings and infrastructure, the potential for casualties, they work primarily from the surface record. They map fault lines visible at or near the surface. They measure the length of fault segments. They use that length to estimate the maximum magnitude a fault can produce. The size of a fault constrains the size of the earthquake. Continental mantle earthquakes do not follow that framework. Their source faults, if they have faults at all in the conventional sense, are 70 to 90 kilometers underground, invisible to surface mapping, not detectable by the standard methods used to build seismic hazard models. As Koper's team noted, there is currently no way to estimate the maximum possible magnitude of a CME using existing methods. The tools built to measure crustal earthquake hazard simply do not apply. The 1979 Randolph event was magnitude 3.8. The 2025 Messer earthquake was magnitude 4.1. Both were too small and too deep to be felt at the surface. Nobody was hurt. No damage was reported. But magnitude 3.8 and 4.1 do not represent upper limits. They represent the only examples scientists have confirmed so far, and in a category of seismic events that was not formally recognized until 2026, the sample size is 9 earthquakes over nearly 5 decades. On September 10, 2025, while Koper's team is still completing their analysis of the historical record, the ground beneath Messer, Utah moved again. Magnitude 4.1. Depth, 68 kilometers. More than 20 kilometers below the Moho, in the upper mantle, in the same region where the 1979 event had occurred. It produced no aftershocks. It was felt by nobody on the surface. And it confirmed in real time that continental mantle earthquakes are not historical curiosities. They are ongoing. They are happening now. They will happen again. George Zant, the young postdoctoral researcher who first calculated that 90-kilometer depth in 1979, is now in his 70s. He spent most of his career doing seismology that had nothing to do with this anomaly. For 45 years, his findings sat in a short abstract in a journal that almost nobody read. What he found was real the whole time. The earthquake that should have been impossible was not impossible. The rule it appeared to violate was not a law of nature. It was the boundary of what scientists had observed so far. Beneath Utah, deep in rock that flows on timescales of millions of years, something is still breaking. Scientists do not yet know what. They do not know how often. They do not know how large it can get. They only know it is real. And they only know that because one researcher in 1979 looked at numbers that made no sense and wrote them down anyway.